Good afternoon. We have seen some amazingly smart speakers today, am I right? Yes, let's hear it for them. I'm sorry to say I cannot promise you that I will say any smart things this afternoon. All I can promise you is some very high-grade stupidity. Does anybody here watch this show? Raise your hand if you watch this show. All right. I love this show. It's got all the best parts. It has science, engineering, and explosions. And when you have a bunch of kids, you can't watch so many shows that have explosions anymore, but you can still watch MythBusters. And it's educational. So I'm a big fan of this show. I'm particularly a fan of this guy, Jamie HYNEMAN. He's one of the hosts. And if you watch the show, you know that of the two, he's kind of the quiet one. He's kind of introverted and doesn't so much like talking to the camera. He's kind of grumpy, doesn't like people messing with his stuff. I like Jamie because he reminds me of me. And when I see him on the show, it makes me feel better because if he can get in front of the camera, then I feel better about getting on a stage. And so, in honor of Jamie HYNEMAN, and in order to borrow a little of his mojo, I've brought a prop with me today. How's that? Well, there's your problem. So, it looks like pretty much everyone's familiar with the show, but if there are one or two people that aren't familiar with the premise of the show, I want to run through it really quickly. They take a common myth, like Archimedes used mirrors to focus the rays of the sun on an invading fleet and burn it up. They devise an experiment to test whether that myth could have some truth in it. Then they usually build something. They usually have to build a test rig of some kind, or maybe multiple test rigs. There's a lot of building on the show. And next, they test the myth. They see if they can reproduce the circumstances of the myth. For instance, get 500 high school students to focus mirrors on a boat and put Jamie on it to make things a little more interesting. Then finally, they make a determination. Was the myth confirmed? Was it at least plausible? Or was it totally busted? If you watch the show long enough, you start to pick up on a subtext, which is that the real reason they do this is as an excuse to play with really cool toys. I like playing with cool toys too. One of the toys that I play with a lot is Ruby, and I do a lot of talking about Ruby at conferences and other venues. And so I could talk about Ruby, but the thing is, this is a multidisciplinary, multilingual conference. I think there are probably people here representing many different languages and ecosystems, and so I didn't want to kind of silo it down to Ruby. I wanted to talk about something which is more of a lingua franca, something that we all share in common. So what could be a lingua franca, some technology that we all have in common? Well, what I thought of is the shell. I think most programmers have used the shell. Who here has used the shell? And I think if you've used the shell on a modern operating system, you have probably used Bash, the born-again shell. So I thought we'd talk about Bash today. And because this is a MythBusters-themed talk, I thought we could maybe come up with a myth about Bash that we could bust. Now, what sort of myth could we bust about Bash? How about this one? You've all heard this, right? Bash isn't web scale. All right, maybe you haven't heard it in those terms before, but I've always felt like, Bash is something that you use for quick hacks. You can write little scripts, but when you want to write a real program, you need to use a real programming language. I've always thought that. I've never actually put it to the test. Just kind of assumed it. So let's put this to the test, which means we're going to need to build something. What to build? Well, how about that classic example application, a single-page web chat application backed by a Bash script? Not by a Ruby program, not by Java, but by Bash. So I did, and it looks like this. Gorgeous, isn't it? And you can find the code at that URL there. And there, I'm done. You can all go drink now. All right. Actually, what I thought that I would go through for a little while here is I thought I would just show you some of the highlights and some of the things that I learned while I was building this application. In order to write a web application in Bash, we need to serve HTTP. Can we serve HTTP from a Bash script? Well, it turns out we can, using a program called netcat. As its name suggests, it is like cat, but for TCP and UDP sockets. Here is a simple HTTP server using netcat in Bash. We print some header lines and some content. We pipe that data into netcat, NC, and we tell netcat to listen-L to port 8080. And it's going to sit there and listen for a connection on port 8080. Now we can flip over to another terminal, and we can fire up an HTTP client like curl, and we can request that port, and we see hello world. So this worked. We successfully served some data from netcat. If we flip back over to the terminal running netcat, we see this. We see the request headers that came in from curl. So what you can see there is that netcat has basically just plugged that TCP port into our terminal. The output goes to the port, and the input comes back and spits out at our terminal. That's fine for static data, but if this is going to be a web application, we need to serve pages dynamically. We need to respond to different requests and reply appropriately. So how do we do that? Well, that's where things get a little bit tricky, because netcat is really simple, and it's just read-write. Data goes out, data comes in. There's no concept of something like, call this function back when you get a certain kind of request. So we need a way to make netcat dynamic. We need to enable it to branch on the requests that are coming in and take different actions. We need some kind of co-process to work with the netcat process and make decisions for it. It turns out that Bash supports co-processes. And this is something that I did not know before I started writing this program. If we use the coproc command and give it a name for our coprocess and a command to execute, it will start up an asynchronous coprocess for us. Let's go over a little example. Let's say we want an asynchronous coprocess to do a little encryption for us using the ROT13 algorithm. So we say coproc, we give it a name, ROT13, we give it the command, which is just a tr command doing some substitution. And what we get back from that is something that is some output that looks very familiar, because this is the same output that we see when we put an ampersand at the end of a command line and start a command asynchronously. We see a job number and a process ID. We also get a few other things, because Bash takes the name that we gave it and treats it as a shell array variable. Bash has arrays. And what it does is it stuffs some values into that array variable. So if we look at ROT13 sub 0, we see this number 63. We look at ROT13 sub 1, we see this number 60. Well, what are these values, these mysterious numbers? It turns out what they are is file handles. Bash has given us a way to talk to our coprocess by filling in these file handles. 0 is the standard out of that process, and 1 is the standard in of that process. So now we can talk to it. So let's see how we might do that. We could echo some text into our encryptor using standard shell redirection and using those file descriptors to redirect our output into that coprocess. And we could echo some more text into that process. Then we could read a line out and echo that to the screen, and we can see there's our ciphertext. We can read another line out, echo it to the screen, and there's some more ciphertext. So we can see that we've got this coprocess that's working with us. If we're going to start coprocesses, we also need to end them. There's a rude way to do this, which is to kill them, and Bash does provide us with a ROT13 underscore PID variable, which makes this easy. But killing things off is always a little fraught, because you might never know what they're doing when you kill them off. The polite way to kill a process is to close its file handles. And Bash also gives us a way to close file handles. Here's an example where let's say we wanted to start some command, but with its standard input already closed. We would use this funky looking syntax here to say close file handle number 1, which is standard in. Okay, this is all fine and good, but we don't want to close a file handle on a new process. We want to close an existing file handle. Turns out we can do that too. Exec, we usually use exec to start a new program in place of the current one. But as it happens, we can also use exec without any command, and when we do that, bash performs any redirections that we supply to exec in the current bash process. This is another thing I had no idea about before I started digging into this, but it actually has some very interesting applications. For instance, we can temporarily redirect standard input for the script that's running. Maybe its standard input is coming from the keyboard. We can temporarily redirect it to come from file instead, and then redirect it back to come from the keyboard again. So you can actually, redirections don't have to be just at the start of a process. You can perform them in the current process. You can also close file handles. All right, but we don't want to close file handle 63. We want to close whatever is in rot13 sub 1. So we need to do some interpolation there. So we do it like this, except unfortunately this doesn't parse correctly. Bash expands things in the wrong order, and it gets all confused. So what we actually have to do is enclose the whole thing in quotes and then eval it. Simple, right? And this brings me to one of my favorite aspects of programming in Bash, which is that when you're programming in Bash, you can pretend that you're summoning the Elder Gods. All right, so now we have everything we need to use netcat as a coprocess. We can start it up with a coproc command. We can plug it into a request handler. This is a helper function called handle request that we give it the PID, and we use redirection to route the output of netcat into that function and route the output of the function back into netcat. So the function can take in whatever the request is, decide to do something with it, and then spit some output back out to netcat, and netcat can send it off to the browser or the whatever client. And then when we're done with it, we know how to close the file handles. This is a picture of the MythBusters workshop, Jamie's workshop, actually. They do most of their builds in his workshop. It's lined with these amazing shelves that he built that they're covered with these bins from floor to ceiling, and all the bins are neatly labeled, which just brings warmth to my neat freak heart. Sometimes I like to pause and just try to read some of the labels on them. You got your standard stuff like your wheels and your rolled metal, but if you look carefully, there's also a ladder in a bin, which I think is pretty neat. Anyway, speaking of organization, this is going to be a big program, so we're going to need to organize it somehow. And the way to organize a Bash program is with functions, shell functions. Now, I had written shell functions in the past, little one-off shell functions to automate something, and I thought I knew what they were. But it turns out that shell functions are kind of peculiar. They're not like functions in any other programming language I've used. Most programming languages, it's arguments, and you got your arguments, you got your return value, and that's pretty much it. Shell functions are much more like tiny shell scripts. So you have positional parameters in the $1, $2, $*, all those variables, just like a shell script. They have their own redirectable standard in, standard out, and standard error streams, just like a shell script. And just like a shell script, they can't return any kind of structured data. They can only return an integer exit status. So here's how I might have written a function before I understood this. Let's say I wanted to throw my rot13 code into a function. I might have written it something like this. You can see where I'm echoing the first argument, $1, into this pipeline. Here's how I would, and this is how we call it. Just pass in that first argument. That's our clear text. We get our ciphertext out. Here's how I would write it now. Note that the echo is gone. There's no messing around with parameters anymore. It's just the pure command, nothing more. And the way I use that is I echo my clear text into a pipe. I pipe it into that shell function, exactly the same as I would any other command on the command line. They behave just like little bash scripts. By the way, little tangent. you might have noticed, we've seen this code a few times now, you might have noticed that there's this funny looking command in front of the TR that does the text translation called standard buff. And this is something that I learned about while I was writing this. Have you ever found yourself in a situation where you're writing a program and you're trying to run a sub-process as some kind of filter? So you're running a sub-process and you're feeding data into it, and then you're expecting filtered data out of it. Except no matter how much data you feed into it, nothing ever comes out. Have you ever been in that situation? Okay, a few people have seen this. I've run into this in the past, and what I eventually realize is that the filter program has a buffer on the front. And I'm not giving it enough data to fill the buffer, and so it's just sitting there and waiting, and it's not going to put anything out until I fill that buffer up. And this can be incredibly annoying when you're just like feeding little tiny test data in. It's like, why does this work with real data, but it doesn't work with my tiny little test data? It's because I'm not filling the buffer up. So standard buff is this cool little utility. All it does is it modifies the buffers for programs. So you can stick it on the front of a command and modify the command's input and output buffers. In this case, what this says is take this tr command and give it no input buffer at all. So as soon as we put something in, something's going to come out the other end. All right, back to functions. One more thing we need to cover with functions. Variables in Bash are global by default, and I think we all know that that is a recipe for madness in any kind of large program. Fortunately, there are local variables as well. All we have to do is we have to declare them as local, and they will then not leak out of their functions. So there we go. That's how we're going to organize our program. Now, we're also going to need to serve some static files. We're going to need to serve like an index.html, some JavaScript files, maybe some CSS. So we need a way to do this. And one of the problems that we have to solve in doing that is we need to serve them with the correct content type. So typically the way I'd handle this is I'd have some kind of map from file extensions to content types. How can we do this in Bash? Well, as it turns out, Bash has associative arrays, otherwise known as maps or dictionaries or hashes, depending on your programming background. And you declare them with this very obvious syntax of declare -A and then the variable name and then your values. But once you know that syntax, you can define associative arrays in Bash, and you can map things to other things. So once we have that, to look up our content types for a file extension, all we have to do is we have to use the file extension as a key, and we get back our value. We can even supply a default for the case where the key is not found. Yet another thing that I did not know about Bash until I started writing this program. Now, in order to get to look up a file extension, we have to have the file extension, so we need to pull it off of the file name. Turns out there's a very easy way to do this in Bash. What this interesting little expansion syntax here does is it says expand the variable and then throw away everything up to and including the last dot and just return whatever was after that last dot. So this is an incredibly simple way, or quick anyway, way of getting a file extension out of a file name in Bash. Put all that together and you get something like this. We have a local file variable, which we get by prepending the public directory to whatever path was requested. We check to see if it exists. If it exists, we pull out the file extension. We look up the extension in our content type table. We feed back some headers, including that content type. And then we just cat the file to our netcat coprocess, and the file is on its way down to the client. All right, now this is 2014, and we cannot talk about web scale without talking about the actor model. We need some actors in our program, but unfortunately, this is Bash, and we don't exactly have the budget for. Oh, sorry, I got ahead of myself there, and that's what happens when you don't handle asynchrony correctly. Let's go over the two parts of the actor model real quick. For an actor model, you need an asynchronous. You have basically, when you boil it down to its fundamentals, you have an asynchronous process and a queue for communication. But like I said, this is Bash. We don't have the budget for A-list actors. We got to make do with whatever we can find. I don't know if any of you recognize this guy. This is John Agar. He starred in such fine films as The Mole People and Revenge of the Creature. So what are we going to use to put together our B-movie actor model? For the asynchronous process, we will use a subshell. Simple enough. And for our cue, we will use a named pipe, or otherwise known as a FIFO. So here's how we're going to create an actor, or an AGAR, as the case may be. We'll make a little function for creating actors. We'll pull out an actor name and some arguments from the parameters that are given to that. We will create a pipe in a special FIFOs directory, and the pipe is named for the actor. That pipe is going to be dedicated to that actor. Then we spawn the actor. First off, we execute the name as a command, and we feed it whatever arguments were provided, but we also prefix that command with an assignment. So what this says is that in that sub-process, the cue variable will be set to that FIFO, the name of that FIFO that we generated earlier. So now this actor knows where its mailbox is. It knows where to check for messages. We allow that to execute to its conclusion, however long that takes, and then when it's all done, we make sure to clean up after ourselves by removing the FIFO. Now, you might notice that all of this is enclosed in curly braces, which makes it all one unit, one subcommand, and after those curly braces is an ampersand, so this is going to be spawned off asynchronously. It's not going to block the actor generator function. We also define a little send helper. This takes a destination and a message, and it basically just takes the message, pipes it into the appropriate FIFO for the target actor. All right, so to create an actor, we just do this. Let's say we have a main function. We say agar main. Here's our main function. It, too, is very simple. We've got while true, so this is an infinite loop. We delegate off to a helper function called serve with coproc, which sets up that netcat coprocess. With its helper function, and it does that asynchronously, so that doesn't block. But then it stops and tries to read something from its queue. It doesn't care what it reads. It just needs to wait. It needs to wait on that queue until it gets a signal to go on and go ahead and spawn up another server process. Over in the serve with coproc function, we've got some code that looks something like this. It's going to sit there and wait to read one line of the request coming up from an HTTP client. As soon as it gets a request from that client, it knows, okay, now this actor, is dedicated to serving this request. And so it sends main a message, go ahead and continue, go ahead and spawn up another server process to catch the next request. So take that, Erlang. We got our own actors. All right. In order for this to be a useful program, we need to persist data. Now, the data that needs to be persisted, remember, this is a chat application, so the data is in the form of messages, and the messages look something like this. They're generated on the client side. It's very easy to generate JSON on the client side, and they look like this. You've got a name field for the person that sent the message and some text of the message itself. Now, since we are storing JSON data, we're going to use everyone's favorite NoSQL document database to store it, Postgres. Our schema is very simple. We have a table of messages. It's got a primary key. It has some content. And notice that the type of the content is not a string, it's not text, it's not a blob. It is JSON, because Postgres has built-in support for JSON data. And this enables some really cool stuff, which we'll see in a moment. We also have a posted at timestamp, which defaults to now, so we don't have to manually set that. It'll set itself. All right, let's load some example data into our database. Notice that we are using JSON inside of strings. And now let's query our database. This starts out looking like an ordinary SQL query. We've got our select content, and we got some sort of funny arrow thing. What that funny arrow thing is, it's one of Postgres' specialized operators for digging into JSON data. What this says is, select into that content column, into the JSON data inside that content column, and look for a text key. because we're interested in only the text of the records in that column. And then it says where content, funny arrow, name equals Bullwinkle. And that's saying, again, select into that JSON data inside that column and look for only the JSON data blobs where there's a name key and the value is Bullwinkle. So Postgres enables us to dig directly into our JSON data without having to do any parsing in our program, which is great because our program is written in Bash, and I really don't want to figure out how to parse JSON in Bash. All right, let's return to our myth. The myth was Bash isn't web scale. So how'd we do? Well, I got it working, barely. It's slow. It uses processes for everything, so it's not exactly the lightest weight thing in the world. It's unreliable. It works about half the time. There are some bugs in it that I was never able to track down why they were happening. For some reason, it only works in Firefox. I have no idea why. Leaks processes like a sieve. It turns out that FIFOs are a huge pain to work with, at least for building an actor model, because they love to block. Give them half a chance and they will block both the writer and the reader. And then frees up your whole program. And Netcat's not the greatest thing to serve HTTP requests with. When I look at this final analysis, I have to say, this whole thing seems like it was a terrible idea. I don't know if you can tell what this is. This is a car whose wheels have been replaced with manhole covers. I think it's fair to say that running a web application on Bash is like running a car on manhole covers. I don't recommend it. I'm going to have to call it. Myth confirmed. Bash is not web scale. Which brings an obvious question to mind. What was the point of all this? We started off with a dumb idea, and we pursued it, and it turned out in the end that it was indeed a dumb idea. So, why bother? And I wish I could say that this is the dumbest idea that I've ever heard of using Bash, but somebody else went and wrote a whole Lisp in Bash. This is not a joke. And back in 2001, somebody wrote an x86 assembler in Bash. Now, I have a problem. When I see stuff like this, when I see somebody post on a forum, I wrote a web application in Bash, there's this part of my mind that says, what a stupid idea. What a pointless waste of time. Why would you waste time doing something like that that's so obviously dumb? Here's another one for the stupid idea file. Julia Evans, having no previous systems programming experience, decided one day that she wanted to answer the question, how do kernels work? And she decided that she would answer the question by building one. And as if that wasn't hard enough, she decided that she would build one in a brand new, undocumented, highly volatile language fresh out of Mozilla called Rust. And she did. She built it over a series of 6 weeks. She built it. She blogged copiously about it. If you haven't seen these blog posts, you can go to her website. I highly recommend checking them out. They're phenomenal. She wrote about the process. She wrote about getting it to the point where it could turn the screen red instead of blue. I had the great privilege of talking to Julia just a few days ago on the Ruby Rogues podcast, and she had some interesting things to say about the value of this kind of experimentation. One of the things she said was, if you ask questions that are really dumb, eventually you know things. And I think this is kind of profound, because there are a lot of people there are some questions that every programmer, or almost every programmer, is asking. Like, how do I make the next Instagram? Maybe not in so many words, but when you see the great interest in whatever the web framework of the day is, that's basically the question that's being asked. How do I make the next Instagram? It's not so often that you see somebody asking, how do I write a kernel? And interestingly, a couple of weeks after she finished this project, Julia got an email from a team that wanted to recruit her for a kernel hacking project. Now, remember, she had no previous systems programming experience. So on one level, that seems like a really dumb thing to do. But on another level, I think it was really smart. Because here's someone who was willing to ask the question, how do I write a kernel? And was willing to pursue it to its logical conclusion, and was willing to potentially make a fool of herself by blogging about it. And as a result, here was someone with some knowledge and a level of perspective about the tools that she works with that not every programmer has. One of the ways that we can set ourselves apart, that we can differentiate ourselves as programmers, is by having outlier knowledge. By being able to take two disparate bits of information learned in two random different places and put them together in a new way. And you never know what bits of outlier knowledge you're going to be able to put together like that in some new way that's going to solve a problem really well. And you don't get that kind of outlier knowledge without asking outlier questions. At the end of the episode in which the MythBusters tested the Archimedes mirror myth for the third time, and for the third time failed to set a ship on fire despite having 500 highly polished mirrors focused on it, Jamie HYNEMAN had some things to say. He said this: MythBusters is about experimentation, not demonstration. And he said that while he was out there on that boat, which was conspicuously not catching fire, he had a realization. He realized that while the mirrors were not hot enough to set his boat on fire, they were extremely dazzling and distracting and confusing. And he realized that maybe that was the grain of truth to this whole myth, that maybe Archimedes didn't set an invading fleet on fire, but maybe he threw off their navigation and threw off their aim by using this method of distracting and dazzling with mirrors. And he said he would not have had that realization if he hadn't been out there on the boat experiencing it. And then he said this: when we experiment, when we try things, and when we fail, we start to ask why, and that's when we learn. What did I get out of this dumb idea? Well, I got a story to tell. I also got a chance to get my hands dirty with some technologies that normally I'm kind of at a distance from. Normally I'm working through abstractions, but I wrote SQL by hand and I wrote HTTP by hand, and as a result, I'm more comfortable doing that now. I don't feel as afraid to get in there and just write those things. I learned about tools that I didn't know about before, or I didn't know their full capabilities before, like Netcat and PSQL and Standard Buff. And man-in-the-middle proxy, which I didn't get a chance to show you, but it's super cool. Look it up. I learned about, and these are all tools that I know I'm going to be using in the future. I'm going to use them to solve problems in the future, and then they're going to be in my toolbox because I was fooling around with them in this dumb bash web server. And I got to become more comfortable with bash scripting. I got to a level where I think, next time I need to automate some little thing, I'll be a lot more ready and able to throw together a bash script to do it. I don't think I'll ever write a program as big as this one again, but I think I'll be using bash functions more. And finally, it was fun. And I really think that it's important to carve out some time every week to code on stuff that's just plain fun. It gets our minds out of the ruts that they fall into when we're at work. It stretches our minds out and just makes us think of new things. So if I leave you with anything, it's this. Next time you get a stupid idea, an outlier question, pursue it. Make some time to do the experiment and see where you get. Whether it's a web server in Bash or strapping JTOW rockets to a car, if it involves rockets, please be safe. But make some time to pursue that dumb idea, see where it takes you. It will probably fail, but you will almost certainly learn something useful along the way. And if nothing else, you'll get a story to tell. So as I said, the code can be found there. If you want to check it out. If you dig Ruby, I make Ruby screencasts for a living. RubyTopics.com is the URL for that. And feel free to get in touch with me. Thank you very much.